Hello people! Today I'm building a fan controller with an Arduino along with a small 0.96 OLED display. You can find an index of the topics in the description down here, so you can jump directly to it if you're not interested into a certain topic. So a short word from our sponsor. I wish I had a sponsor, so if you want to become one, feel free. Up to the display. The display shows you temperature, the fan speed and the power setting of the fan, along with a graph of the temperature of the last 20 minutes. You might ask, why don't you just use the fan controllers on the mainboard? It's a good question. Well, on the mainboard, the fans can only be controlled by either the CPU or mainboard temperature. On a water cooling system, this does not make any sense, as the thermal capacity of the water is around 3,300 times higher than air, depending on the air pressure and temperature itself, but anyhow, it's a lot more. Adding to the thermal capacity, you have the copper and the aluminium of the water blocks, fittings and the radiator itself. If you're not interested into a detailed explanation of this, skip to here. Somewhere there. There's a minute. So, from your CPU away into the water block and of course out of the GPU as well into the water, you have a specific heat transfer which is dependent on the delta of the water temperature of the CPU die and the water temperature. The speed in which this transfer happens is given by the material and the architecture of the water block, with copper being a very good heat conductor with around 398 watts per Kelvin meter, and aluminium coming in at 234 watt per Kelvin meter. You have a way better option. This would be diamond with around, I think, 2,300 watt per Kelvin meter. So I really wonder why we don't just make water blocks out of diamond. I don't know. So if your CPU and water are the same temperature, no heat is being transferred. If the difference increases, the heat transfer starts to work. Where with an air-based CPU cooler, this will need the fans to spin up earlier to dissipate the heat, the water will get only slightly warmer with its high thermal mass. We actually can run the system for a very long time. Here's the math behind for those who really want to know it. Just to mention, my pump is a very small DCLT and I'm only running it around 28% PWM mode. Yes, that's enough for a system like this with a 2080 Super and a Ryzen 3900. It's not a problem. The only downside is you won't get small bubbles out and the air out of the system after filling it up. So my CPU is around 105 watts of thermal loss, my GPU around 250 watts of thermal loss, and that's adding up to around 350 watts of thermal mass. In my system I have around 1,200 grams of water, and if you go into the calculations, which I will show up now, you can see how much joule we will need to heat up this amount of water. And I have around 1.4 kilograms of water in the water blocks, in the radiator and fittings and everything. Might be aluminium, but yeah, just assume it's 1.4 kilograms. And we will need also 11,885 joules for that, along to the 110,500 joules for the water. In total, that's 122,000 joules that we need. And now, if we assume that we are running the system at full speed all the time, and so basically watt is joule second, so we can just take the watt we had and make it joule here. We divide our 22,000 joules by our 350 joules, and we end up at a time of 344 seconds, which is roughly 6 minutes. So this is assuming my water has been at 33 degrees at the beginning and my temp limit would be 55 degrees, then otherwise my PETG hard tubing might melt, and this is really bad. The assumption is also that we are not having any heat loss somewhere else. So in general, if you run a water cooling system, you will always have heat dissipating from the backplate of the GPU, from the blocks itself, from the tubing itself, and even if the fans are not spinning, the radiator is of course giving away heat because it's just going up and out of the complete casing. If we do the math being idle, The CPU is around 20 watts. There's data with around 17 watts and the GPU also around 20 watts. Taking this data from the internet, and I haven't measured it myself, but at the end we end up around 40 watts of heat that is produced by these two components. And then if you take again our 122,000 joules and divide this by our 40 joules per second that we have right now, we end up with 50 minutes from 33 to 55 degrees, 35 to 55 degrees. And here you can see a time lapse of my PC starting at 37 degrees, all fans turn off. And it took around 30 minutes to get up to 42 degrees, which clearly indicates how high the capacity of the water and the metal is, and also how high the heat dissipation of the whole system passively is. The temperature of the air above the tower got up to 33.4 degrees at around 40 degrees water temperature, for example. And there you can see that the math I did before is not right, because even if the fans are not running, we have a lot of heat dissipation from the tubes and, as I said, water plugs radiators. I've been using the PC in the background for office use, let's call it like this, so browsing, surfing, watching some movies. And you can see even here, through the CPU and GPU temps, they jumped a bit during office use. The water temp wasn't rising nearly at all, it's just a stable line slowly going up. And here's an overview of the temperatures on all places, not on every place, but on many places in the case. And you can see with the air incoming at around 24 degrees and outgoing at 35 degrees, how much energy the air has to take away from the water, while the temps from the radiator inlet to the outlet only fell from 35.81 to 34.44 degrees, which is not that much. Taking into account the thermal capacity of air is way less than of water. The CPU sensor was showering around 48 degrees, while the block itself was around 35.41 on the inside. The GPU showed 36 degrees, while the block was around 35.69 degrees, which indicates I'm getting the heat out of my CPU very bad, and I got to investigate that. Maybe I did something wrong with the thermal paste, but yeah, it's not optimum. I hope that sums up why we are not interested into measuring the GPU, CPU or mainboard temperature. We are only interested into the water temperature, because that's where the heat goes out of the case, and this is where our fans depend on. So to build a fan controller, you need the following components. An NTC temp sensor, wait a minute, it's something like this. And basically it's a 10K resistor at 25 degrees. And if the temperature changes on this casing here, also the resistance changes. And this is how you can measure the temperature in the water. You will need 10K resistors as well with an Arduino Nano. Any Arduino might work, but this is just the smallest version that I have at home. I think it's the smallest version available. And if you want, you can take a small SPI OLED 0.96 inch display. You can get them in China and also on eBay, quite cheap. There's a lot of different versions of those, so we will make another video on that, because it's quite complicated sometimes, how you can get them to run, which voltage you need, how you can speak to them, if they work at all, and so on. The quality is even differing. So let's go through the whole process. So the fan is connected to the 12-volt rail via a yellow cable, while the blue cable, PWM, goes to pin D3 of the Arduino. And this is to control the power of the fan. And the green cable connects to one of the 10K resistors that is connected to 5 volts. This is called a pull-up configuration. This connection then goes further into pin D2, and so basically the voltage is pulled up via the 10K resistor on the pin D2, and all the fan does is to lower it slowly and kind of introduce a signal into the Arduino. The NTC is connected with one leg to ground, while the other leg goes to pin A5. Pin A5 is then again connected via 10K resistor to 3.3 volts and analog reference. This is also a pull-up configuration or a voltage divider where the two 10K resistors divide the voltage into, so basically 3.3 volts into 1.64 volts at 25 degrees because of the NTC having 10K resistance. We are using 3.3 volts as a reference as the voltage is much more stable than the 5 volt rail in general. In a PC, so in a computer, we might not have this issue as the 5 volts are coming from a very stable power supply, but in general it's a good approach. We will tell the Arduino to reference all analog inputs at 3.3 volts via the code later. So the display is connected like this. You take the MOSI D1 on the SPI display and connect it to pin 8. You connect the clock D0 on the SPI displays. They have a different naming for that on pin 7. DC goes to pin 10. CS goes to pin 11. Reset goes to pin 9. Ground is connected to 5 and the voltage plus VCC is connected to 6. Strangely enough, my display works without applying any voltage to VCC. You can in fact leave ground and VCC unconnected and the display still works. I assume it works by the voltage supplied by the SPI bus alone, but I haven't investigated that. I have some displays from China that do that, and I have not analyzed this yet. I will investigate this in the next video along with some other stuff about the 0.96 inch OLED displays. OLED displays are in general more vulnerable to burn in and losing brightness. I've had mine running just for 2 weeks, so I cannot give you feedback on that yet, how it's burning in or if it's losing brightness already. So this is the complete configuration on a breadboard. All you have to do is upload the code in the description and it should start working. You can later solder everything together on a small package to put into a live system. It is the same setup as on the breadboard, but you can solder the resistors directly onto the Arduino Nano, of course, and the display can be soldered onto the back of the Nano as well. So that we get a small package that you can easily put into your computer. I ran out of leaded solder and I must admit I really hate lead-free solder. Leaded solder was the best and worked a million times better. I miss it. I really miss leaded solder. I like lead and I hate this word. So I just ordered a bunch of leaded solder from China. I know it's probably not the best for nature and everything, but it works so much better. One thing to notice, leave the cables to the Nano longer as you want. Trust me, hiding a longer cable is easier than extending it later. Why? Because you want to place the display along with the Arduino somewhere in your case, while the connections are somewhere hidden on the back of your mainboard, in the lower compartment of your tower, or wherever you want. The fan and the Nano are just taking the power directly from an SATA connector. You can also use an older EDE connector. Just make it 5 volts red, 12 volts yellow, and the ground is always black. I later used a small magnet between the Arduino's USB connector and my radiator to hold it in place. In the code itself, you can set your parameters on top. The values of your 10K resistors is best controlled with a multimeter to get an accurate reading. So not every 10K resistor is exactly 10K, they might be 9500 plus minus 10% very often. I also prepared a water bath for the NTC to check its resistance at exactly 25 volts, and it's also not 10K. So just take a bowl of water, make it 25 degrees, and then I took a fever thermometer and checked the temperature and the resistance, and just wrote it down and also changed that in the code. With the BCO efficient, you have to play around a little bit. It's different from NTC to NTC, and it's basically the curve on which the resistance change. You can get its value easily by first calibrating it to 25 degrees as stated above. Then you can go ahead and heat up the water to 40, 55, 35 degrees, whatever, and just measure it and then play around with the BCO efficient until you get the correct value read out on the display. Your min fan temp is set to the 1% duty of the fan, and the max fan temp sets the temp when the fan reaches 100%. Be careful, if you have PGG hard tubing, I would not recommend going above 55 as the PGG gets softened then, and the PGG gets compressed in the fittings, so you might have leaks. So minimum duty, so this is used to define the fan's minimum power. So even if there's basically the system's just booted up, you can set the minimum level where the fans will run on. I would always run them on a little bit to keep components as voltage regulators, for example, in the case supplied with a little air, while it is in fact not needed for the radiator. And most fans do not spin at very slow settings here. The ones that I tested need around 12 to 16 duty, that's around 15 to 20% power. Duty goes from 0 to 79, and this has to do with the PWM mode configured on the Arduino's pin. And this is how you build an Arduino based fan controller. So guys, like, share and subscribe, and see you next time.